Everybody. Welcome to this presentation. Today we're going to be taking a look at what I've described in kind of general terms, which is open source data analysis. And we're actually going to take a look at two examples. And I'm sure that with a little bit of work, you could easily replicate what we're going to cover. And one of the great things about open source applications is that you don't have to buy a license. There still is a license involved, but getting a license for open source software doesn't require making a purchase in the same sense that, say, like an app like Microsoft Excel, might. And this is actually a really good thing because it makes it easy to experiment. And there's many sort of applications for what we'll look at. And I wanted to start off by talking a little bit about how an open source language, computer language, can be utilized to estimate a transcendental number known as Euler's number. And Euler's number is a special number. It appears in a lot of different contexts. And so like if you're working in, say, performing a statistical analysis of some kind, a number like E you might find. And also in when we talk about mathematics, that's a pretty broad subject. And there are lots of different contexts in which you'll find Euler's number. So I'm just going to jump right into the slides here. Towards the end of the slides, I'll provide you guys with a link where you can get the materials that we're going to look at today. And the great thing about open source software is that, anybody can use it, and people also participate in the development of later versions. And that's something that, open source software, really, is makes it really appealing. So we have this concept of tactical and strategic decision making. In most contexts, we want to be able to make informed decisions. And there is kind of a distinction between decisions that we make on a short-term basis and decisions that we make on a long-term basis. And so decisions that we make kind of like in an immediate sense are described as tactical decisions. And then decisions that we make to influence things over the long term are sometimes called strategic decisions. So when we make tactical decisions, it could be helpful to have our goal in mind, which is what we want the end result of our work to be. And so it's in this sense that the decisions that we make on a short-term basis directly influence whether or not we're able to achieve our overall objective. And so here we're looking at an example comparing tactical decision to strategic decision. And so our long-term objective in this example is to approximate Euler's number. And Euler's number, if you look here in this slide, you'll notice this person's name. It's Leonard Euler, and he is sometimes identified as the father of graph theory. And graph theory today is relevant in a lot of different contexts. So, people working in math study graphs, people in industry utilize graphs to make decisions. And so it looks like his name looks like it's might be pronounced Euler, but it's actually pronounced Euler. And so the number E, which is a mathematical constant, is specified just using a lowercase e like this. And if our long-term or strategic goal is to approximate Euler's number, we actually have to be able to calculate something else known as factorial in order to be able to approximate E. So our overall objective is to approximate E, and our short-term goal at this point is to calculate factorial, because of course factorial, which we'll look at in a moment, is part of the way E is estimated. So the question at this point is, what is factorial? And factorial is expressed using an exclamation point, which is sometimes just called a bang. And I think calling an exclamation point a bang is probably a practice in computing. It may not be that way in other contexts. And so when we write a factorial, we specify an integer value, positive integer value, and we follow it with an exclamation point or a bang. And so 5 factorial is written as 5 times 4 times 3 times 2 times 1. And if we calculate the product, we end up with 120. And so our short-term goal, the tactical sort of decision we're making here to calculate factorial, is facilitated by a high-level, object-oriented, open source programming language called Java. And some of you guys may have heard of Java before. And so we can actually calculate factorial in Java in this manner. What we're looking at here is a function. And so in the world of functions, at least in the context of computing, we are able to build sort of like a recipe or an algorithm for calculating factorial. And the interesting thing is, Java comes with a method for calculating factorial. However, even though I could have just utilized a pre-existing version of factorial to calculate the factorial, I wanted to do it this way just to have some extra control over the way things actually work. And the reason why, one reason why we kind of have to write a function is because we're using a special data type called a big decimal. And a big decimal supports operations on floating point numbers. We're basically talking about 128 bits. So if we take 2 and we raise it to the power of 128, that gives us an approximation on the range of values that we can represent. And by using this special type big decimal, we're able to make a better estimation of E. And we haven't actually looked at how we're estimating E yet. And that, of course, is our overall objective. We're just examining kind of like something along the way to being able to estimate E. And if you look at this function, it's kind of a special function because we're using a control structure known as recursion. And when we talk about a recursive function, it's simply a function that calls itself. So if you look at the function here, notice that the name of the method is factorial, and in the method itself, we're calling the same method. And what you'll notice here is we're using this parameter, which is also a big decimal, and we're using this parameter to limit the number of times the method can call itself. Because, of course, we don't want to just, keep calling the method. Once this argument n is equal to 0, notice we're returning 1. And the math here is, I guess, might be a little bit difficult to understand. Instead of using arithmetic operators, we're utilizing methods which belong to the big decimal class. And so notice here we're subtracting 1 from n with each recursive call. And so it wouldn't be too difficult to prove that if n is initially a positive integer and we repeatedly subtract 1 from the integer, that eventually the integer will be equal to 0. And it's precisely at that point when n is equal to 0 that we're just returning 1. And so notice here in the recursive call, we're again relying upon big decimal methods to perform some simple math. We are adjusting n by 1. We're subtracting 1 from n. And so n gets a little bit smaller with the next recursive call. And n, of course, is approaching 0. And then we're multiplying what this recursive call returns by n. And this is precisely how a factorial is calculated. And this will give us the exact result. And I think, I've already kind of tested this out, and it does appear to work properly. And this is kind of our short-term or tactical objective to calculate factorial. And then once we've built this method for calculating factorial as a recursive method, we can then focus on our strategic goal of estimating E. And we accomplish the estimation of E in a similar manner to the way we calculated the factorial. And so this something special about the function or method that appears here is that we're also specifying that we would like 128 bits. And that's actually a bit bigger than the standard numeric types that are built into Java. So this method, calculate E, is also a recursive method. And the reason why we describe it as recursive is because, given the right condition, this method, calculate E, is going to call or invoke itself. And again, we are relying upon methods defined in the big decimal class to perform some simple math. And what we're doing here is we're utilizing what's sometimes referred to as an accumulator. And the accumulator variable is this variable here, calc. And so the way we estimate E, directly builds upon the way we calculate the factorial. And since we're using 128 bits to represent the numbers that we're calculating, or I should say the number, the main number here is calc. And so initially we have to select a scale. And the scale is this parameter here, this big decimal n. And so we can utilize this parameter to effectively limit the number of recursive calls that we make. And if we make, say, 1,000 recursive calls, we end up with a really good estimation of E. And, you might be wondering what this program that we've looked at outputs. So we actually have the output here. Notice we're prompted to enter the scale. So we've specified a scale of 1,000. And so at a scale of 1,000, we have this estimate of E here. And so by utilizing the big decimal class, we can actually estimate E to an additional 18 digits. So according to Java, specifically a constant in the math library, E is estimated here. And notice that the output from the example that we're looking at has an additional 18 digits. And I actually, one of the difficulties is knowing whether one has the right estimate or not. And so I think, well, I looked around, I think I checked out the Wikipedia page on E, and in that page, there's a fairly lengthy estimate of E. And I did confirm that these additional digits that the method we're looking at calculates, it's basically a number that could potentially be utilized in contexts in which E is utilized. And this might, make calculations in which E occurs more accurate. And this, I also wanted to share the math behind this example that we're looking at. We basically have a sum of a series, I guess, a series of fractions. So inside of the parentheses here, we have a product series in which this is essentially factorial. This is the way factorial is defined. And what we're doing is we're summing a series of products. So if we write the first three terms, we end up with an arithmetic expression like this. And you can see that the first, I guess, value we're calculating is when n is equal to 1. And if we would like a better estimate on E, it's definitely possible. However, it would require additional work to be able to actually let n get large. Of course, in the world of computing, when we're talking about a mathematical concept like infinity, infinity doesn't exist in computing. There's some languages define a value which exceeds any representable value as infinity. But there's really no such thing as a number called infinity. So even though in this notation here we're summing to infinity, the understanding is that we might only be going to 1,000, like we did in the example that we're looking at. And so it makes sense to think about how this type of work can actually benefit us. So we've estimated E using Java, and the realization is that this is an example of automation. And the algorithm that we built performs work that we would, otherwise have to perform ourselves. And also, the fact that the estimate the algorithm produces is more accurate than E as defined in Java's math library. This basically means that computations in which E occurs might also be made more accurate. And of course, this can make a difference. The one thing to keep in mind, though, is we're using a special numeric type called a big decimal. And it makes writing computations a little more difficult because we can't simply rely upon built-in arithmetic operators. Instead, we have to use functions of the big decimal class to perform operations that we would otherwise perform using, simple arithmetic operators: addition, subtraction, multiplication, and division. So we're talking about open source software. Java is an open source language, and it's really just an introduction to the main part of what we're looking at today, which is a package known as GNU Octave. GNU is a recursive name. GNU stands for GNU's Not Unix. And GNU Octave has been around for quite some time. And it's software really that anybody can utilize. License does not have a price tag associated with it. And it's always being improved. Documentation is comprehensive. There's built-in documentation, and there's also the GNU website where we can find documentation on all aspects of this app that we're going to look at. And like I was saying earlier, when we're working with open source software, we get the opportunity to participate in the development of the app. And this actually kind of makes it possible for interesting things to happen. So instead of, this concept of a company like Microsoft, building software and selling licenses, Octave is actually, in my opinion, it's somewhat refreshing because, I don't have to buy a license to do work in Octave. And so Octave is a really effective way to do data analysis. And Octave is actually very similar to MathWorks MATLAB. And of course, the difference is Octave does not require the purchase of a license. And we're actually going to look at software that runs in the browser called Octave Online. And this web-based integrated development environment, or IDE, is offered under the Affero General Public License, or AGPL. And most scripts that one might write in MATLAB will run in Octave Online. So here is a link to Octave Online. And I'm just going to, for a moment, just jump over here to my browser. And I wanted to show you guys what Octave Online looks like. Using Octave Online doesn't require buying a license. It's basically just Octave running in the cloud. And we have this web-based interface in which we can write what are commonly referred to as scripts. And they're basically kind of like 4 components to this interface. Over here at the left, we have our file explorer. These files can be saved to your Google Drive. So when you first go to this website, octaveonline.net, it's a good idea to create a login. This enables you to save your files in the cloud. And you can see I have several files over here. And in the this section here, just to the right of the file explorer, we have our editor. And you can see that there's I've already written a script here. And we can actually run this script. Notice this option up here, just above the editor, that enables us to run the script. And this is actually kind of an interesting script that I've been working on. Once back in early March, when attention was paid to the development of the coronavirus, I wanted to put some effort into keeping track of the numbers. So we actually have two files. If we go back to the file explorer over here, notice we have this data file, which is just called p.csv. CSV is short for comma separated values. It's a fairly common file format. You'll find it in other contexts as well. And this file, p.csv, is a listing of death counts. So I've been keeping track of death counts. I've also been keeping track of the infection count as well. And you can see these files are growing. I've just been visiting the New York Times US coronavirus page to collect these statistics. And that's the way I've been collecting the data. I could potentially automate the collection of the data. However, that would require programming in a language like Python. It could potentially be done in Java. The difficulty automating the collection of data from a website like the New York Times is that the New York Times has a policy on what are referred to as robots. So what's referred to as a robot is a program that just, periodically visits a web page, parses the web page, extracts data, and then puts the data in a file. And it's not difficult to do that. However, most websites have something that's referred to as a robots policy. And the robots policy basically defines which parts of the website can be scraped. And I'm fairly certain that a better idea as far as data collection for this type of analysis is concerned is just to collect the data by hand. And that's what I've been doing. Once or twice a day, I visit the New York Times US coronavirus page, and I put in the death count and I put in the infected count. And so what we have here is a graph. Let me just see if I can make this a little bit bigger so you can see it. We have this graph, and there are actually two statistics. We have the number of people infected, which is represented by this blue line. And then we also have the death count, which is represented by these turquoise bars. And you can see I've also put a label on the y-axis. I put a label on the x-axis. And I've also put a title on the graph, coronavirus in the USA. And so this is one way you could use software like Octave Online to do analysis. And it's really easy to do this kind of work if you'd like to experiment with Octave Online. All you have to do is put this URL up here in your browser, and you can create an account. Doesn't cost anything. And then something else I also wanted to mention is if you're not comfortable working in the cloud like this, it is also possible to install Octave locally. And Octave can be run on most platforms, Unix, flavors of Linux, Mac OS, and also Windows. I'm just going to go back to the slides for a sec here. and we're looking at the preview here. And one thing that's important to mention about Octave is that the way numbers are represented. So if we have a series of data, we can represent a series of data as what's referred to as a vector. If we have a table of data or a grid of numbers is represented as a matrix. And if we have like a single value is represented as a scalar. And the interesting thing about Octave is that even a scalar is essentially represented as a matrix. So even though we have this distinction between vector, matrix, and scalar, the realization is that internally, all numbers are represented as matrices. And there's also official documentation. You can go to this website to read up on the various sorts of analysis that can be performed with Octave. And documentation is also available in the IDE. I'm just going to go back for a moment to Octave Online. And notice underneath our output, we have this prompt here, this flashing cursor. And this is commonly referred to as the interpreter. And we can actually type commands into the interpreter. So if we say want to read up on the max function, we could type like man max. Oh, it's actually, I'm sorry, I think it's help max. Yeah, there we go. So when we type help max, we basically get the output that describes the way the max function works. Something else that's also possible, if you'd like a more comprehensive description of a function, is you could type doc max, and notice we get a link. And if we open this link, this provides us with a page in which we can look at more comprehensive documentation on the max function. So you basically have two choices when you'd like to read up on a specific function. You could either type help followed by the name of the function, or you could type doc followed by the name of the function. Help is kind of a bit more succinct, and the doc page gets into a little bit more detail than the help page does. So I'm just going to go back over here for a moment to the slides again. And one of the things I wanted to also discuss is what we can do in Octave that we can't do in software, say like Microsoft Excel. Octave actually has some of the same limitations as other proprietary apps utilized for performing data analysis. Some of these limitations include, only so much primary and secondary memory, and the fact, which we've touched upon today, that we can only represent a fixed range of numeric values. And then also with Octave, we encounter a native language that takes a bit of time to learn. However, the refreshing thing here is a license for Octave doesn't require a purchase in the same sense a license for a similar proprietary app might. And here is that plot we were looking at earlier. This is an example of Octave's plotting capabilities. And creating plots is pretty straightforward. And I've also, in these slides, I've provided a couple resources for those of you guys who are interested in experimenting with Octave. There's a link to my website where you can find a zip file that contains the Octave scripts that we were looking at today in Octave Online. You'll also find these slides and the data that I've been collecting in those files. The y.csv file contains infected count, and the p.csv file contains the death counts. And there's also a link here to GNU's site if you would prefer to install and run Octave locally. Installing Octave locally isn't too terribly difficult, and Octave is available for Unix, Linux, Mac OS, and also Windows.